Hello. Yeah, hello everyone, and welcome to today's live interactive session on geology and soil mechanics. Today is the 11th week discussion session that we'll be having today, and in the previous class we went through a huge number of topics, and in the last class we solved actually some problems related to the topic of earth pressure theories, right? We solved some problems on earth pressure theories. In today's session, what we are going to do is that we are going to actually solve some more problems from the earth pressure theory part, and then what we are going to do is that then actually we are going to solve some problems regarding the these stresses at a point in the soil. Okay, so how the stress distribution happens, and that you will see, and we are going to solve some problems regarding that. So let us start one by one. Let us see what we have actually. All right. So so in the last this last theory class, actually these things were discussed with you. So one is the Coulomb's earth pressure theory, and then the stresses in soil. So Coulomb earth pressure theory means what? So generally, when we have a retaining wall, what we do? We generally consider that the friction between there is no friction between the wall and the soil, right? But in Coulomb's theory, what we do, we actually assume that there is going to be some uh, friction between the soil and the wall. Alright, there is going to be some friction between the soil and the wall. Also, what we uh, assume is that the backfill is not straight, it is at some angle. So for that we have a different expression for Ka and Kp as well. So if you want to use Coulomb's theory, if you consider that the wall is rough, then what we need to do, you need to use these modified expressions for the coefficient of earth pressures. Okay. Now let us come to stresses of soil. So in stresses of soil means what? Say you have the soil, and at the surface of the soil you have some kind of loading. So how can we get the stress at any point? Okay, at any point, at any depth, at any point below the surface, at any depth, what will be the stresses due to this applied external load on the surface? So some load is actually applied on the surface, and due to that load, due to that load, what will be the stresses generated at certain depth in the soil at certain point that we need to find out. So this is actually given by this earth, the stresses in soils. How to get that? That was actually given by Oceanics and Westergaard. So these are the two main basic theories that were given by Bosenic and Westergaard. So these two theories are actually these theories actually give you some analytical expression using which you can find out the stresses at any point in the soil. Okay, okay. So there are some assumptions. Okay, I will write those assumptions for you. So for Boussinesq's theory, the assumption are that the soil is elastic So soil is elastic, homogeneous, isotropic. Elastic means elastic, you can understand it won't go into plastic state. Then homogeneous means properties are same at all points. Isotropic means in all directions the properties are same. And semi-infinite means see the soil we are considering that it's just bounded by the ground surface. So in this direction it's infinite, in this direction it's infinite, in this direction it's infinite. Okay, so that's why we are calling this as semi-infinite. Then Hooke's law is obeyed, self weight ignored, initially constraints. So these are the actually basic assumptions. There are some more assumptions, but these are the main basic assumptions of our bosonics. All right. So apart from the bosonics theory, there are some. There is a theory called the Westergaard. So the Westergaard theory is quite similar. So this Westergaard theory is actually quite similar. Westergaard theory is quite similar to bosonics theory, but there are some extra, you can say some extra assumptions, okay, that are done. So those are actually, write it for you. Soil is composed of numerous closely spaced horizontal layers of negligible thickness of an infinite rigid material. So we assume that the soil is composed of like this in layers of infinitely rigid material. Okay, and this rigid material permits only downward deformation. Means what? It assumes that in the lateral direction the strain the strain is actually zero. That means in lateral direction the Poisson's ratio is actually zero. The Poisson's ratio is actually zero. Okay, because it considers that in the lateral direction there is no strain. Okay, and it permits deformation only in the vertical direction. So laterally you are considering that there won't be any strain, there won't be any deformation. Only in the vertical direction there will be some deformation. Okay, that means what? That means the Poisson's ratio is zero. All right. So these are the basic assumptions of these two theories. All right. So we'll be solving some problems regarding that. Okay, where you will be directly using the expressions given derived from these theories. Okay, we won't be deriving that one by one, so that you can do it by yourself by seeing proper textbooks, standard textbooks. Or what we are going to do is that we will be directly using the we are going to directly use the expressions that are derived from Bosonics and Westergaard's theory for different loading conditions, and then we are going to use those to solve the problems. Okay. Okay, so let us start solving the problems on one. So first, what we will be doing is that we will be solving some problems regarding this. What to say this earth pressure theories. Okay, we will be solving some problems from earth pressure theories, and after that, we will be coming to this stresses at the soil. That part we are going to solve some problems. All right. So let us see this question: the cohesionless soil with a void ratio, a portionless soil with a void ratio of 0.6 and G is equal to 2.65 exists at a site where the water table is located at a depth 2 meter below the ground level, assuming a okay a portionless soil with a void ratio of 0.6 and G 2.65 exists at a site where the water table is located at the depth 2 meter below the ground level. Okay, assuming value of coefficient of earth pressure is equal to 1, so they should be actually 0.5. Calculate the earth pressure at rest. Total soil depth is given as, okay, the questionless soil with a void ratio is given, G is given, so water table depth is given, total depth of the soil, total thickness of the soil is given, and the earth pressure coefficient is also. So I have to calculate the earth pressure at rest. So this is very easy. So first what we do, we calculate the dry unit weight of, okay. So these should, you should be able to do this in a second now, right? Because these are the basic, these are from the first chapter. So all these things you should be able to do very easily now. Okay. Here we have the water table. Alright. So top portion, you know, like this, you will have the variation gamma dry, and below what will be this? Hmm? Correct. Hmm. So this portion plus we have for water, right? So we have 1, 2, 3, 4. Okay. This will be 16.5 P2, same. How much? Right? 2 into 3 because this height is 3. Right? So the total P is how much? Please calculate. Please add all this. Please add all this. See how much is the total P. Total earth pressure. Okay. So it is acting at some height here, right? So now we need to find this Y. What? So P1 is what? 16.25 into 2 by 3 plus 3 plus second one is 22.77. Okay, divided by total, that is P, come out as alright. So this is how we need to solve this. Now let us see the next problem. This is also similar, but here we will be having three layers. So I will just draw the figure for you. Okay, so this is the figure. So there are three layers, and all three layers have actually different K value, and we need to find the passive thrust, not the active, the passive pressure we need to find out. Okay, so layer AB. Seven 25, this will be 2.46, and the last layer. Okay, so these are the various earth pressure values. Okay, so we found out the earth pressure coefficient values for the different layers. All the three layers we have different coefficients. As the friction angle differs, the earth pressure coefficient also changes. All right, so now next you have to focus on finding out the earth pressures, right? So now for AB portion, okay, one more thing I forgot to draw there. We actually have a water table at this depth. Okay, so first for AB layer is 3 meters, right? So let's call it one. So this one will be how much? KP is 3.69 into gamma. Gamma is given 17 into 3. Okay. Therefore, the next layer. So next layer, we're gonna have two parts. The first part will be this. It will be 3.69. It's not 3.69. Extremely sorry. So the earth pressure is coefficient is 2.46. 2.46 into 17 into 3. Okay. Plus the other part 2.46 into 20 20 is given as the saturated. So here we have saturated as 20. So gamma submerged is 20 minus 0.81 is equal to 10.19. Okay. So 2, 3. Okay. Third, and also one more we have in this layer, the water. So you should not forget. Okay. All right. Sorry. Yeah. So after that we have one more layer. So what is the K for 2.0? Okay. Alright, so these are the total stationary points. So we have these 6 components. So the total P, total earth pressure, we need to add all these 6 components up. So now let us do it. So P1, so I will just directly write all the values. Alright. So P1 is what? Square. So this is going to be so check all these values by yourselves. Okay, check the do it yourself and then match whether check whether whatever I am writing you are getting it or not. Okay, so match all these values by yourself. 3 4, this is 5, right? 3 4. So total P will be total P, if we add all these pressures are, it will be 17. Okay, now y directly I will just write all this. Gamma test 3 okay. So this is how you have to solve it. So generally what happens in these kind of problems where people make mistake is that they forget to add this part or this part. Okay, generally this happens. So you should not make mistakes in that. Slowly, steadily solve these problems, very slowly, very carefully solve all these problems. Consider all the stresses that we have to consider. Do not miss any of these. All right. So slowly and carefully, whenever you solve these kinds of problem, be very careful. Okay, otherwise you will make mistake. So be extremely cautious and be very careful how to solve. Let us go to the next problem. A 5-meter high vertical wall supports a saturated cohesive soil with horizontal backfill. The top 3 meter is a unit weight of 17 kilonewton per meter cube. Cohesion 15 kPa. Bottom 2 meter is unit weight of 19.2 kN per meter cube and cohesion 22. If tension cracks developed, then what would be the total active thrust? Tension crack developed means what? The top portion is the bottom triangle will come, right, in picture. And we have to find out what will be the total active thrust and then total pressure based that you can do, right? So let us just draw the picture, whatever. So let's say this is the wall, right? So since it is a saturated cohesive soil, Ka will be 0 for both the layers. So phi is 0 we are considering. So Ka will be 0. Right? Now, now what is the expression for the active earth pressure? That is, at any z, this is the expression. So what you are getting, not 0, what did I write? I am extremely sorry. K is 1, right? Yeah, K is 1. Okay, so this we can write as uh, gamma z minus plus. Okay, now z naught. So if you remember what was z naught, z naught is the depth at which I don't know the we can one term for the z naught is depth of tension correct, and the other term for z naught is the depth at which the active earth pressure is actually 0. Okay, so I can write 2 c by gamma root over k. So 2 c by gamma. It is 1.76 meters. Okay, so this much actually we got. All right, now let us draw the stress diagrams. So this is 3 meter. This. Okay. So at the top, our variation will be something like this. Okay. So from here to here, this is 1.76 meter. And what is this value? What is this value? 2ic minus 2ic. So this is minus. So this is minus 30 pp. Okay. Now what is this value? At a depth of 3 meters. So put z equal to 3. So gamma means what? 17 into 3 minus 2 into 15. 17 into 3 minus 2 into 15. If we put in this expression, 17 into 3 minus 2 into 15. So this one will be 21 kp. So this is plus portion. Okay. Now for the bottom layer. This is for the upper layer. So now for the bottom layer, one thing that is fixed is 17. So now we are going for the bottom layer, right? So the bottom layer, one part will be coming from this. So how much will be this? This is nothing but 3 into 17. Okay, just considering the upper layer surcharge, we are doing 3 into 17 into K2. So what is K2? It is 1. So it is nothing but 3 into 17. This is positive. Plus, along with that, again you will be having this. So it is minus twice. So the minus 2 into 19.2 now. So now here Just a second. I think the solution there is some mistake. So I'm just trying to see that. Aha. Okay. Okay. Understood. So actually C is this one, right? 22.5 actually. Okay, so in my head I was thinking it is 19.2. That's why I was thinking why is it not matching? Sorry, the C is 22.5. So here it will be how much? 2 into 45, and then at some depth, at 2 meter depth, it will be how much? Something like this. This is how much? This is 19.2 into 2 minus 2 into 22.5. That is 6 minus 6.6. Okay, so its total portion is minus. So now we need to calculate. Now see. Now in the question, so this is the pressure diagrams what we calculated. Okay. Now the question is, we have to find out the pressure, active pressure when tension cracks develop. So when tension cracks actually develop, this portion we can remove. Okay, so what in our calculation what we'll be doing, we'll be just adding this, this and this. Okay, so let us do that. Let's call it P1. This one will be 1, 2, 3. So P1 I can write half into 21 into 30. So into P2 right, 3 into 17 into 2, 6 into 17, 102, correct. Then P3 so total P is equal to okay. And now what we need to do, one more thing that you need to find out is the point of action, right? So point of action y Now I will tell you. Divided by 63. So it is 1.24. 6.6. So our P will be acting somewhere here. Okay, the P will be acting somewhere here. Alright, so take care of the signs, because when negative this cohesive soils comes into picture, the chances are that this negative portion might create some confusion. So always take care of the sign, always include the sign in your calculation, then there are no chances of mistake. Do slowly, step by step, then you will see that there won't be any chances of mistake. Okay, do very slowly, then everything will be fine. Okay, let us see the next problem. A smooth vertical retaining wall 4 meter high, pushed against solid friction angle 20 degree. C is equal to 20 kPa. Unit weight is 20 kg per meter cube. Find total lateral thrust if horizontal thrust carries surcharge of 60 kPa. Okay. Mm, so we surcharge 60 kPa. Okay, this is 4 meter and phi is 20 degrees. So pushed again. So you can see the smooth vertical wall is pushed against soil. If the wall is pushed against the soil, so this is the wall, this is the soil. So the wall is pushed against. The wall is pushed against the soil. Okay, that is passive condition. So we need to find the passive pressures. The wall is actually pushed against the soil. So passive condition is developing. If wall moves away from the soil, active condition. If wall is pushed towards the soil, then passive condition. Okay. So first we will find Kp. Okay, so this is the expression, right? So now let us do the first thing that will come into picture is due to the surcharge. Okay, with the surcharge you will have this 60 into 2. Okay, all right. Then next next we can write this part twice root over kPa part. It is also constant all throughout the height, right? This is twice c root kp, and then last we can have this variation. Okay, now calculate p1, p2, p3. Please find it out. Please calculate. I'll be back in a minute. Please calculate. So I hope you calculated these values. Right, just sum up the areas. You will get the values of P1, P2, P3 as usual. So please do that. So P1 will be P2 will be P3 will be okay. So total P done. We got the total P. Now next task is to find the Y. Into how much? 4 by 2 means 2. Okay. So this is the final result. Next problem. A 5-meter high retaining wall has a granular soil backfill with a level top. Okay, granular soil means sandy soil C is equal to 0, phi we have. The retaining wall face makes an angle of 85 degree with the base. Retaining wall face is 85, okay. The unit weight is given, phi is given, delta is, so delta is nothing but the friction angle between the soil and the wall. Calculate active thrust using Coulomb's method. So now we cannot use Rankine's method, we have to use Coulomb's Ka and Kp, whatever K, earth pressure coefficient. Okay. So we have the tuning something like this. Okay, this is 5 meters. This is actually 85 degrees. Okay, so let us call this angle as theta. So theta is nothing but 180 minus plus okay, 5 degrees. Now beta is 0. What is beta? The angle made by the soil with this backfill, top layer of backfill soil. So that is written the level with top. That means beta is 0 degree. Other values you have delta 10 degree. Then phi we have. Right. So these values we have. Now Ka, I will write it down. Okay. This square. So if you put all the values, please check, please do this. Put all the values and check how much you are getting. Put all the values, theta, beta, delta, phi. Check how much the K, how much is the K. This will come out as 0. So then we can find out P. So calculate this. Okay, find this out. Next problem. A vertical wall height 7.5 meter is having cohesionless soil at the back, having saturated unit weight as 22.5 kilonewton per meter cube. Pressure angle is given. The water table behind the wall is at 3 meter below the top. A top 3 meter soil is also saturated due to capillary moisture. Find the total thrust and point of application. Okay. So let us draw this. All problems are quite similar. Okay. So this is 3 meter. This is submerged 2.5 minus 7.81. Okay, this is one. Now it is given that the top portion of the soil is also due to capillary moisture. So capillary raise, so capillary raise will be negative. Some negative pressure will also be there. Okay, some negative pressure will be there. So this is what minus and below here we will be having this part. Okay, so total P just a second, we check the calculation once. So calculate all, okay, calculate all these values, also calculate this one also. Then sum of p calculate, then find y. Okay, so do same. Okay, use the same procedure and find this out. Now actually let us go to the second part. Okay, second part. So there are some more problems we will be solving in the 12th lecture or 13th lecture, whatever. We will be solving that later. So now let us solve this second part, because lot of problems from this returning wall we have solved. So now that's why, so let us just solve some problems from the next part, that is this stress at a point in the soil. Let us use this bosonics and Westergaard theory. Using those things, let us solve some of the problems. So we have a concentrated load of 2500 kN is applied at the ground surface. Determine the vertical stress at the point P at a depth 5 meter, but at a horizontal position of 4 meter from the axis of load. Also, percentage increase of the point is directly. Okay. So we have, say this is the top layer of the round surface. Okay. Load of 2500 kN is acting. So first we need to find it at this point P. So due to this 2500 kilonewton load, how much is the vertical stress developed at this point P? That we need to find out. So, so generally what happens, the behavior is something like this. So at the center it is maximum, that is stress, and then it goes on reducing on the both the sides. Okay. So let us find gamma z. So the expression for gamma z is 3q by r is 4, r is the radial distance, I is the depth. So this will be, now if r is equal to 0, if the point is here, then what is the stress? So higher stress, obviously just below the point of loading we will be having higher stress, right? Just below the point of loading, obviously we will be having higher stress. So what is the percentage increase? Percentage increase, uh, yeah, percentage increase will be 47.75 244. So just below it is 244% higher than whatever it is in the 4 meter side. Okay. Next problem, two columns A and B are situated 6 meter apart. Column A transfers a load of 500 kilonewton and column B a load of 250 kilonewton. Determine the resultant vertical stress on a horizontal plane 20 meter below the ground surface and at a point vertically below point P. So this is point A, this is point. This is at 6 meter below. So now at a horizontal plane 20 meter below, so at this point you need to find it below B. At this point. Okay, so first the contribution of A, let us find the contribution of A. R is how much? 6. Okay, now contribution of B. So very less, right? So therefore total stress, increase in stress, okay, so this is how you do. So the next problem, almost similar to the previous one, a three-legged tower. Now 3 points will be there. That means three-legged tower forms an equilateral triangle in a plane of side 3 meter. The total weight of the tower is 450 kN and equally carried by all its legs. Compute the increase in vertical stress caused in the soil by the installation of the tower at a depth of 4.5 meter directly below one of the leg of the tower. Okay. Okay, load on each leg. So now the arrangement is something like this, right? Equilateral triangle. Right? Now we need to find, where do we need to find out the stress? Where do we need to compute the increase in voltage? Directly below, so below any one of the leg we need to find out, right? Below any one of the leg we need to find out. So this point, so contribution of this one, this one, this one, this one, and this one, this one. There are three things we need to do. So this is the contribution of C lag on C itself. Okay, below it. That's why 0. R is 0. Okay. Next, come. That will be equal to sigma 3. Therefore, total okay, very simple. Now let us see this problem. An infinite line load of 600 kN per meter exists. Okay, line load is there. Before we solve problems regarding point load, now instead of point load, we are having line load. So infinite line load of 600 kN per meter exists. Determine vertical stress at points A with coordinates x equal to 5 meter and z equal to 4 meter. Okay. So here, thing like this. Okay, so this is x, this side, this is 6. Like this we have. The coordinates of the point A is given x equal to 5 and z equal to 4. So here and say here. Okay. So this is meter and this is, sorry, x equal to 5. This is 5 meter and z is 4 meter. Okay, so that this is the point. Alright, this is the point PC. 4. Alright, so this is the expression for the line load. Okay. Now the next problem is same, but now we have two parallel line loads. So try to solve this problem. I will give you some time. try to solve same expression you have to use, just a little different. Same, okay? The similar problem you have solved already. So try to solve this one. Try to solve this one. Two parallel line loads 1500 kilonewton per meter and 500 kilonewton per meter are separated by 5 meter. Find stress at a point 4 meter below ground level and 5 meter away from away horizontally from the 500 kilonewton per meter. Okay, so try to find same concept. Try to calculate. Calculate. Very easy, right? Same. Just the distances will vary. 2 times you have to calculate and then add it up. That's all. That's all you have to do. Quite simple. See, if I draw in 2D, this will be same. So this is actually a line load, right? But I'm just drawing this 2D. Okay, so we need to find here. This is 5 meter, this is 4 meter. So at this point we need to find. Okay. Right. So okay, quite simple. Direct, you have to use the formula. That's all. Next, yeah. A loading of 50 kPa is acting on an annular foundation of width 5 meter and inside diameter is 10 meter. Find the vertical stress intensity of the 10 meter below the center of the foundation. So annular foundation means something like this. Okay, like this, annular foundation. Okay, just we have the foundation. Now this much, this is 5 meter, and the inside dia, this is 10 meter. Okay, we need to find the vertical density at a point below the center at a depth of 10 meter. Okay, at a depth of 10 meter below the center, we need to find the releasing stress. The loading in this annular disc that is given, that is 50 kPa. That is the loading in that area. Now, what we can do, we can find out for a circular loading, outer circular loading, complete loading, and we can deduct from the between. That will give us, so the two circles we can consider, right? Two circles we can consider. One with diameter 10 plus 5 plus 5. This is 20 meter. Another with diameter 10 meter. So we can calculate for this, and then deduct, so that we get for that annular portion only, the common portion only, right? So Q is 50 kPa, our outer 10 meter, our inner radius, not diameter, radius. Okay, this is radius I am writing. Meter, and Z is 10 meter. Okay, 10 meter. Z is equal to Q. Okay, so put the values and find it out. Let us see how much is it is coming. So put all the values in place of Q, you put 50, R not 10, R I 5, Z is 10 meters. So put all the values carefully in the expression and to calculate. So let us see how much is it is coming. Calculate this, solve this. How much are you getting? It should be 18.10. Okay, so this is the result. Now let us come to the next problem. A 2-meter wide strip footing is placed. Determine the vertical stress at 0.2 meter below the center of the strip. Okay, so what we have a 2-meter strip footing, so it's long like this. Long area is there. Strip footing. The loading is given as meters. Okay. All right. This is 2 meters. So below 2-meter center, here we need to find out. Okay, so depth is 2 meter below. Is the ship footing is like this long, so below 2 meter depth you need to find out. Is the so this is theta, this is theta by 2. Okay, this is say this is 2 meter. Now Z is nothing but q by pi okay. Now tan theta by 2, so like this it's there, right? Tan theta by is this by this, by 2. That's it. Yes. Okay, so therefore this is the vertical stress. Right? Now let us come to the next problem. So this problem will be the last problem for today. So here we have to calculate the intensity of a stress point located at a depth 2.5 meters due to just a second. Calculate the intensity of stress point located at the depth of 2.5 meters due to a load of 2 kp over a footing area of 4 meters. So we have a footing area. So we have a footing like this. Okay. Okay. Now we need to calculate the intensity point located 2.5 meter below. So depth is 2.5 meter, and okay, we need to calculate somewhere the depth of 2.5 meter. Okay. Now the point P is the location of the point P I am going to draw. So the point P is actually located here. So 2.5 meter below this point, this particular point which I have marked, below this point P, 2.5 meter below this point, whatever I have marked, there you have to find out the stress. Okay, there you have to find out the stress. So for that, what we will do is that we are going to divide this into some, like this, divide this. So 1, 2, 3, 4. So 4 sub areas we are going to divide this completely. So this is given 2 meter. This is also 2 meter. This is also 2 meter, and this is 3 meter. Okay. Now how to do that? So a long this relation is there, a comprehensive relation is there. That relation we are going to use to find this thing. Okay. So a comprehensive relation is there which gives the stress at a point below a corner of a footing. So that we are going to use to find. So though the point does not lie on the corner, we have drawn some pseudo footings. Drawn for pseudo footings. So you can see the point P lies the corners of the pseudo footings, right? So using that concept, a relation that is there, which gives us the stress below a corner of the footing, using that relation, we are going to solve this problem. Okay. Just give me a second. Just give me 1 second. Okay. Yeah. So let us do that. So now let us go for area 1 and 3 m. So there is a term m. M is nothing but L by Z. So what is length? Length is 2. Z is the depth 2.5. Then N is B by Z. What is B? Width, again 2. Right? Next for area 2 and 4. M. M is what? L by Z. L is what? 3. 3 by 2.5. N is B by Z. B is how much? B is 2. Width is 2 by 2.5. So these are the necessary parameters. Now the K value, K. So sigma is nothing but K times the total stress. Alright. So K, this K is given by this expression. Okay, so this is the expression. This expression. So we will be having the expression like this: gamma z is equal to k1 plus k2 plus k3 plus k4 times our total load. So loading is 250 kPa. Not 2 kPa, it's 250 kPa. Okay, times 250. This will be the final answer. Now we need to find all these k1, k2, k3, k4. So k1 and k3 are equal. So k1 and k3 are equal. K1 is equal to k3. So this we have to find out now. This k1 and k3 we need to find out. So for that you can see some terms are repeating, right? Like m square plus n square, then m square n square. These terms are actually repetitive terms. So what we can do, you can easily calculate separately those terms and then put in the expression. So then it will be easier. So what is mn? Mn is what? 0.8 into 0.8 for area 1 and 2, right? So then m square plus n square plus 1 we can calculate. Now calculate m square plus n square plus 2 you can calculate. Okay, so now what we will do, we'll put in this expression. So now let us look at this tan inverse wala expression. This tan inverse expression, tan inverse 2mn is 2 into 0.64 into m square n square 2.28 square 1 by 2 by m square plus n square means 1.28. So so see here m square plus n square plus 1 whole thing is there, right? So I can write directly 2.28 minus mn minus 0.64 square. Okay, so calculate this, see how much you are getting. Calculate this one. So at a glance, at first, the formula looks actually very intimidating, right? But don't get intimidated. If you see, if you just break it in parts and solve, then it will be quite easy for you. Okay. So this tan inverse actually comes as 45.94 dB. So in radians, you need to convert it to radians. So in radians, it will be 0.8. Now K 1, so now finally k1 is equal to k3 is equal to 1 by 4 pi, put all the thing twice mn, 2 into 0.64 into 2.28 by n square plus n square plus 1, 2.28 by 0.64 square into 3.28 by 2.28 plus 0.8. So if you do this, it will come out as 1.4 pi okay. So after that, similarly you have to do for K2 and K4. So for K2 and K4, calculate Mn. 1.2 and 0.8, right? 1.2 into 0.8. Nine six. right? And similarly we can find out tan inverse 2 into 0.6 so this will come as tan inverse almost one radian. Okay, finally what you have to do, okay, sorry, and by 4 by something you find this out plus 1, so finally this one will come out as 0. Okay, so check this one, check check this one once. Finally to 250. Okay, so finally we can get the value like this. Okay, sigma z like this. Okay, so a little bit lengthy but quite easy, right? Quite easy. Please check this. Okay, it's quite easy. So like this we need to solve the problem. Okay, so I hope you have understood everything, right? It was everything was clear to you, and so with this we will end today's class. And if you have, we already actually have 2 more minutes left, so I am here. So if you have any doubts regarding anything, you can ask me. So in today's session, to sum up, we solved some problems regarding the passive pressure, active pressure, all those things, Coulomb's theory, and then we solved problems regarding this Bose-Einstein Westergaard theory, right? So in the next class also we will be solving some more problems regarding retaining mass and all this stuff, and we will be just seeing overall whatever we have studied. And in the 13th class, that will be a division class again. One more division class we will be having on, so next Friday. So today is 5th. So next Friday 12th same time, 12th April same time, Friday 12th April Friday from 6 p.m. to 8 p.m. again we will be having our 12th discussion session. Okay, from 6 p.m. to 8 p.m. there will be solving some more problems from all the topics whatever you have studied. And in the last session, that is on 13th, on Saturday, for 1 hour from 12 noon to 1 p.m., what we will be doing is that we will be having a 1 hour sum up session, summary session, where we will just discuss among ourselves, okay, whatever you have studied. And if you have any doubt, you can ask me. Okay, we will try not to solve any problems. Last we will keep everything as a, like a casual discussion session. And I will just sum up again. I will just revise everything from first to last, whatever you have studied, so that it will be actually beneficial to you. All right. So I hope you are understanding, you are following all the lectures, and you are understanding, are able to understand whatever is being taught to you, and you should understand actually, because everything is being almost taught twice to you, right? Twice, not thrice to you. Once by the course instructor, and twice by myself and one my colleague, right? So you have lots and lots of problems, right? Lots and lots of problems that were solved, okay, in the class, then in the two discussion sessions. Lots of problems you have got. You should have a large question bank with you, right? So try to solve these problems again, and try to solve these problems yourselves once again, so that all the concepts are clear to you, and also that in the exam, whenever you try to solve easily, you can solve it, right? So you have a good practice, good hold over the problems. So with this, we will be actually ending today's session. So thank you so much for attending, and uh, hope to see you in the next discussion session. That is on the 12th April, Friday, from 6 p.m. to 8 p.m. Thank you. Have a good day. Thank you for attending. And if you have any doubt, please feel free to contact me anytime. And thank you. And good night. Thank you.